In this video, we're going to learn about series circuit and the three rules. Now, first step is to see how the river system is related to the circuit over here. As mentioned in the previous video, the cell has an EMF of 10 volts, so it's equivalent to a pump that pumps water up to a height of 10 meters. And if I were to label this point here as A, and just before it enters R1, let it be B. So this part here is just copper wire and is represented by the point A here, and the section of the river where there's no change in height, that is your copper wire. This is point B, and then enters into R1. When the current flows into fixed resistor R1, there is a height drop in the system, in the river system. So this corresponds to your R1 and this corresponds to your R2. So let's label this as C, and this section here is D. So C corresponds to this part here, and D will correspond to here. Then after coming out from R2, let's label it as E, and lastly, just before it enters into the negative terminal of the cell, let's call it F. Okay, so you can see that from E to F, this is the lowest portion of the river. This is like your 0 meters. Okay, so here is like throughout is 10 volt everywhere you are at any point until point B, that is 10 volt, and point E onwards all the way until F, it will be 0 volt over here. So that's basically how you see it. Next, let's talk about the first rule, finding the total effective resistance of a series circuit. Now, R1 and R2, they are connected in series, they are side by side, and there's only one path in which the current will flow. So to find the total effective resistance, or just total resistance of the whole circuit, basically you just add them up. So R equals to R1 plus R2, and it's that simple. Next, let's talk about current. But let's address a misconception here. A lot of students think that when the currents enter into R1 and when it comes out, there will be a reduction in the current, which is wrong. As you can see, there's only one path in which the current flows. The current remains constant. So if you look at the river system over here, you can see that the water flow is equivalent to your current, and there's only one path in which the water will flow, and the water flow is constant throughout the whole system. So if I were to label this as I1, here is I2, and over here is I3, their relationship will be I1 equals to I2 equals to I3. Then how about the current? If you want to find here the current flowing through R1 and the current flowing through R2, if you look at the system once again, you will understand that they are all the same. The current remains constant throughout the whole circuit. But then you might ask, then will the current change here? The current that comes out from the battery, will it change? Yes, of course. It all depends on the total effective resistance of the whole circuit. So if the total effective resistance is higher, then the current that flows through the series circuit will be lower to start with. So, but remember this, at any point in the series circuit, the current remains constant. The third rule is about potential difference. For a series circuit, the rule is the sum of potential difference across all the components in series must be equals to the EMF. In other words, for example, the potential difference across R1, let it be V1, and let's say it's 4 volt. That means to say the potential difference across R2, let it be V2, it has to be 6 volt, because the sum of potential difference of the components in series, that means V1 plus V2, it has to be equal to the EMF of the circuit, no more, no less. Now, let's relate to the river system. Previously, when the current flows through R1, there's a potential difference of 4 volt. In the river system, that means a height difference of 4 meters. So that means to say, as it passes through R1, there will be a drop in voltage of 4 volt, or in other words 4 meters. So from point A here, previously we have established that this is 10 meters, and throughout the copper wire from A to B, everywhere will be 10 meters. Over here will be 10 meters. Then after passing through R1, there's a height drop of 4 meters. So that means to say at point C, now it remains 6 meters. So point C, now the voltage there is 6 volt. And at point B, the voltage is 10 volt. If you minus off, that's why you say there's a difference, potential difference, voltage difference of 4 volt. That's what it means. So at point D here, likewise is copper wire. From C to D, it will remain as 6 meter, 6 volt. And after passing through R2, it will be ground 0, 0 meters, 0 volt over here. That's why once again, there's a difference in the voltage. We call it potential difference of 6 volt or a height difference of 6 volt. So that means to say, as you pass through R2, there's a height drop of 6 meter or 6 volt. So that's the real understanding of potential difference. You see as a height difference in the reverse system. So lastly, if you add the potential difference of V2 and the potential difference of V1, you add them together, it's like you add up all the height difference, it must be equal to the original height of the reverse system, which is the EMF 10 volt. So that's why you have this relationship.